Yeah, before we start, any question for last week lecture? Question? Last week lecture? The assignment I posted. Any question? Ask. Yeah. Hmm. Right. Hmm. That's quite true. That's why I put one first. That's quite true. Yeah. One way to do question one is to use question two. So I purposely put question one because I want you to try a different way to prove it. Yeah. Sorry. Yeah, it should be quite straightforward for question one. You just for one way, you just assume there's an inverse, and then you prove one and on two. Then once you have one and on two, you define an inverse. Yeah, yeah, it's okay. Yeah. Yeah, of course, one quick way is to use question two, but question two requires some technical stuff, which we will discuss today. Can we start? First, Jimbo. Yeah. Okay. Let's start. So I start with this slide here. So every kind of science, if it has only reached a certain degree of maturity, automatically becomes a part of mathematics. You know who is this guy? This old guy. Cannot recognize. Can't see clearly. I mean, this gesture, you should kind of guess already who is this guy with this bald head. This is huh? Sorry. Uh, I mean, not every bald head is famous. Right. Okay. So this guy is Hubert. Yeah, Hubert Space Hubert. Yeah, yeah, with the head. Yeah, yes, yes, yes. Usually has the head one. Yes. Yeah. I think he liked to touch his forehead like this, but yeah. So this agree to what I said last time. Right? So if you want to like ask about why, ask about some why something is true or something is true, then this will become mathematics, right? Okay. Yeah. So this is the highest highest level of academic. Actually, mathematics is the hardest course in this world. Okay, so it's not surprising that you feel that maths is hard. Okay, uh, one question I want to address before we go into the lecture today is about this sentence that Gary mentioned last time. If GF is surjective, then G is surjective. Okay, we don't really need to know about what F is doing. Okay, so how you imagine this? So imagine you should have a tree set as the domain and codomain of G and F. For example, like this. So we have a map, let's say going from the right to left, F, G, okay. And then we have a composite map, which is GF. Right. Okay. So you should imagine that, say, this domain has several things, right? And since GF is surjective, right, means what? Every element there have a pre-image, right? So let's draw some pre-image, something like this. So you want to ask about whether G is surjective. So can you somehow pull this element back, like how you do for GF? Can you do it? What can you do? So you could pull this element back to what GF does, and then you push by F, right? So maybe something like this. Then you can associate this set as the pre-image of the element for the image of G. Does it make sense? Does it make sense? Any question? This. Yeah, so I mean, this is just a generic picture, okay? Just a normal, I mean, just some picture you can think of when you talk about this statement. Okay. Any question? No? Okay. So far, okay. Okay. In that case, we will jump into the axiom of choice. So last time I leave you with a few statements of axiom of choice. Actually, I leave out the sixth statement in the last slide. So which is the most important one you're going to use in your assignment, which is if G, okay, if G is an onto map, right, inverse, okay, such that GF is identity. And to build this map, actually you need axiom of choice to satisfy. Okay. So since we call axiom of choice an axiom, meaning we cannot deduce it from anywhere. Okay. Even from the most recent set theory axiom, we cannot deduce it. So we take it as an axiom. Okay. We assume that it's true. And assume that it is true, then we will get a few very nice statements here. So these are all equivalents. So meaning these all statement can't be true if you don't have an axiom of choice. If you have axiom of choice, then these are just equivalent statement of axiom of choice. So the first axiom of choice we introduce is following Moncrief. Okay, so Moncrief, what does Moncrief say? Given a collection A of a disjoint non-empty set, okay, there is a set C consisting of exactly one element from each element of A. So A is a set. So inside this set are non-empty. So you can find an element. Okay. So C is picking up one element. Okay. So C is exactly what? Is a subset of a union of the set in script A. Okay, such that for every set in script A, C intercept A is an singleton. So meaning you have a script A, okay, inside there. Okay. So when I talk about this one, I want you to imagine. Okay, start imagine. So when I say, oh, there's a script A, so you should think that there's a script A. So what's script A here? It's a, what's it? Disjoint non-empty, collection of disjoint non-empty set. Okay, so meaning you should imagine that inside here there's some other set. Okay, and then in particular these are non-empty. Okay, and okay, so maybe I write a few more. And then they are disjoint. Okay, turn this into something that is useful. Empty. I equal J. Right. And then C is a set that when you intersect each of them, you get a singleton. So meaning you pick one thing from each of these sets. Right? What you're doing is picking one thing from each set. Okay. So meaning it's like you can make infinite choices. And this is not something you can always do. I mean, at least imply from some existent axiom. Okay, so that's why we wrote this as an axiom of choice. Okay, so what does axiom of choice do is you can make infinitely many choices. Okay. So does it make sense for this sentence here? First one. Okay. And second is just a generalization of one. Okay, second is a generalization of one. Instead of talking about destroying non-empty set, we just take non-empty set. Okay, and then we still can make this choice here. Okay, we still can make the choice. Okay, so it's a slight relax of condition from one. Although we phrase it differently here. So here is a function, here is a set, right? So really you should see that what does the set in one do? The set intersect every A, give you one thing. So meaning what? If you fit A to this C, right, you will just get one thing. Okay, a single. Yeah. Okay. So you are like picking an element in A. So this is what the second statement state as the choice function. Okay. Next, the third segment is if you have non-empty set X, okay, there's a function, okay, from the power set of X. So what is power set of X? Anyone can recall what is power set of X? Set of subset, right? Okay, set of all subset of X to X again, such that if you fit a subset of X that is not an empty set, okay, it gives you an element in A. Okay, somewhat similar, right, like a choice function. Okay, if I fit a set to F, and then F give you an element in A. But for 3, we just consider one type of set. Okay, just any non-empty X. 4, if F is a function with a domain A, and then there's another, you can find that there's another function with domain A again, okay, such that if you fit an X from A to H, okay, and HS is non-empty, then F will pick up an element in HS. Again, similar to the choice function, okay, trying to pick something. 5, if a row is a subset of A cross B, okay, is a relation with domain A, okay, then there's a function from A to B such that F is a subset of row. So last time we introduced function as a set. So it makes sense to say that a function is a subset of ordered pairs. I mean, set of ordered pairs here. Because Cartesian product of A and B is the set of ordered pairs such that ordered pair X, Y, or A, B such that A from A, B from. And then the last one is this. If G is a map from B to A is onto, then there exists a F from A to B such that GF is identity. So this actually there are 6 statements, there are equivalents here. All right. Are you guys wake up yet? still on the okay. Still attentive or not? Otherwise, how about we break into groups? Let me see how many people. Okay, let's break into group of three, about three. Okay, maybe you two can be a group. Okay, then you two be a group. Okay, and then maybe group of two then, since you guys are in pair somehow. Okay, let's break into group of two. And how many group are 1, 2, 3, 4, 5, 6? Okay, so we have 6 group here. Okay, so I want you to discuss implication. Okay, some of the implication. Let's use a cooperative work to prove this statement here. So I will prove 1 to 2, and then 2 implies 1 is kind of obvious. So we need 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to maybe somehow back to 2. And we are done. Okay, now 1 or 2, if I can prove 1 to 2, then 2 to 1 is almost immediate. So let's see, 1, 2 to 3 need 1, 3 to 4 need 1, 4 to 5 need 1, 5 to 6 need 1, 6 to 2 need 1. Okay, sorry? 6 to 1 also can, 6 to 2 also can. Because I can straight away do 1 imply if I only have 2. Okay, so we need 1, 2, 3, 4, 5. Okay, we have extra 1, then good. Okay, if I have extra 1, right? So let's say GJ and Lim prove 2 to 3 first. Okay. And then Dingyu and Siyu prove 3 to 4. Okay. And then Sayed and Ziqian prove 4 to 5. And then Jinpo and Yongyan try and prove 5 to 6. And then Brian and what's your name? Ifan. Okay. Try and prove 6 to 2. Okay, if in that case, you two want to try one of them or you want to prove 1 to 2? 1 to 2? Okay, I give you guys about 5 to 10 minutes like that. Okay, at most 10 minutes, and I will call you guys back. If you can manage to prove one, you just try other implication. Okay, you need a time frame. Try and discuss with your friends. What do you need? Okay, what do you need to produce? Can you produce or not? If you produce one, can you check that it's having the property it wants or not? Yeah, you have to check. Mm. Let me think. I guess the word with a domain A, you need everything from A, I think. In normal relation, I think it's like what you say. But say we have domain A already, then probably we should be. Try start from understanding the statement first and then what you need. Then can you find one? Yeah, introduce to each other if you don't know each other yet. Say what's your name? And then you apply this. So since six things, if something they will define a function. You ask something this and this section of function. So I need to somehow define the section such that K3 such the functions the subset of functions. Yeah. So you need to use the system to class 6 so and then we show that right in the others. That you want to so you guys go. You guys go. Any progress? Okay. So let's not do 1 to 2 first. I guess that one is a little bit involved. Let's see who is doing 2 to 3. Who's doing 2 to 3? Okay, how you guys go? Any result already? Yes. Yes, sir. Okay, then let's try. So let's do 2 to 3 first. All right, let's do 2 to 3. Can you tell us what have you tried? Can you tell us what have you tried?
Try to relate.
B. What do you need? Okay. Tell us what's the statement you want to prove, and what you are given, and then what you want to find. Okay, tell us using this way. Okay, using this way to identify what we need to prove. So first, what's the statement you want to prove? Yeah, sure. Let's read it out.
For all non-empty set X, there exists a function f, the f the power set of x to x, such that f is an element of A,
Yeah.
where A is in the power set of x, but then it's not empty set.
In other words, is what? In other words, these are the non-empty subset of X. So meaning what are given? So what's the information that's given before proving? Not collection. It's just one empty set, not collection of them. Right? Just for any non-empty set X. It's just a non-empty set X. There's no collection of them. Too many later. Right. So it's just a non-empty set here. Okay. And then what do you want to find? What do you want to find? You want to find a function. Okay, good. So you want to find a function that do some job. So what's the implication here? What's the implication here? What's the assumption you can take from 2? Yeah. What's the assumption you have from 2? So the statement 2.
For a collection of non-empty set curly B,
Mm-hmm.
there exists a function C that maps from curly B to the union of B,
Mm-hmm.
such that B is an element of
Okay, so 2, what does 2 can do for you? If you input a collection of non-empty set, this 2 will give you a function. Okay, does this 2 function can coincide or not? Okay, so this is our problem here. So what's your approach? How do you define this F? How do you define this F here?
that F would be then C.
So let's try. C.
C given
And
that
then
maps our set of X for any set X for any non-empty set.
okay. So you see, just let F equal to C, right?
Yeah, C.
So I mean, if you want to use 2, right? So you need to produce me collection of non-empty set. So how do you produce? What is B here?
The curly B our set of
Just power set of X? See, B have to satisfy what property? Non-empty set. Power set of X contains what? Sure. But empty set is always a subset of every set. Right? So how take away? So that's why there's a take away thing here. Right? Okay, so let's try. So let's take away the empty set. Okay, so you got this B already. Then by I can produce you a choice function such that this is going from Px cross E to union of everything inside this set. Right? Such that what? Such that C of B inside here, okay, let's write like this, get sent to an element in B. Okay, so this is what we have, right? Now you want to define my F to be just C. Is this enough? Not enough. Yes. Yes. So how?
another empty function and then F is C.
Oh, sure. Okay. So since C only defined for Px cross phi, right? So we simply define what C have to do on empty function, you mean, right? So define, should I say piecewisely? So let's define piecewisely, okay, such that C sends phi to where? One empty set. Let me see. Do you want empty set or? So what does this phi have to set? F have to satisfy? F of this phi have to be an element in phi. Oh, no. Okay, so there's no specification about what does this F have to do on empty set. So then you can, and yeah, you can do literally, wait, cannot do anything, but you have to land in this core domain here. So what do you want to do? Yeah, anything. So what's the anything here? Not empty set is not an element in X. Right. You see this function the codomain is X, right? So I have to go where? I have to go where? Any element. No? Why this work? Because X is non-empty, so you can just pick any one of them. Does it make sense? Does it make sense? So say, so such that because S is empty, there exists like that. Okay? Can or not? Okay. So in the end, we just define F to be our new F to be this C. Okay. That takes on Tx. Yeah. Any question? If any question? Any question? Does everyone make sense of this now? Does everyone make sense? First of all, does your two make sense of this?
The C
Does
that exist?
You define. Why not? Why not? I define. Anything wrong with this definition or not? A unique assignment, right? If I give you a set, you give me one thing in the codomain. If you give me empty set, I give you an element in A. Yeah, I shouldn't write this set of empty set. It's just an empty set. You feed me an empty set, I give you an A. This A is any A in X. It doesn't violate statement 3, right? Because statement 3 doesn't say that where empty set should go. It just says that FA have to be in A for all the A which is non-empty subset of X. Okay. Does everyone got it? Got it or not? So this is kind of a trick. Always we do this trick. We can send some domain element to some fixed element that doesn't create. But we can do this precisely because our X is non-empty. So we can just pick any one of any element of X. And we can do so because X is non-empty. Okay? Others got the question or not? No? Following? Okay. Okay. So next, 3 to 4. Who is doing 3 to 4? Who is doing 3 to 4? Who is doing 3 to 4? G and Yingyu, huh? So what's the statement you want to prove? What's the statement you want to prove? Any one of you? Quick. What? I mean, what's the function to do?
This function
Uh-huh. Okay. Uh-huh.
checks
Okay.
then fx is an element
Yes. Okay. So what's the condition you are given about H?
H is a function based on
Okay, good. So you have a function. Okay, you want to produce another function. Okay, so how about the assumption you have from statement 3?
there is a function f from the power set of x. It is a set. It is in A.
Okay, good. So yeah, so you have 3, but you have to prove 4. Okay. So 3 will produce you a function as well. Okay. So can you make this x appropriate such that it gives you the function you want? Or what's your approach to it? Set x equal to a. Okay. No. You don't ask me. You just do what you want. Okay, and then check whether it's correct or not. Don't ask me whether can or not. Okay. So if I set x equals to a, okay, what happened? So you try to use part 3, right? So by 3, what do you have? You will get a function from PA to A such that EA to A such that what? Such that if you have a say a non-empty subset here, right? So such that this is non-empty, you will get what? You will get an element in X. Okay. So how about F? How about 4? 4 needs what? 4 have a condition here. There's an H here. So how you involve this H? Right? How you involve the H here? If you just do this, is this F what you want or not? What do you want? You see, your Fx have to fit inside where? Hx. So can you make this X to Hx or something like that? Or not? Do you understand what I say? I mean, if you set like this, right? Where's your H? Like there's no H involved here, right? But the new function that you create have to have something to do with Hs, right? Huh? Let them try this. Okay, let them try this. Set x equals to Hs. Okay, let's see what happens. If x equals to Hx, okay, then we are looking at the function from offset from Hx to Hx, right? Okay, and then what? And then, yeah, I think this all. So here become Hx. Okay, but how you define f here? How do you define the f here? So let's say I don't call this f, okay? Let's call this g, so that we don't confuse ourselves. We don't know yet whether this is what we want or not, right? So we have this property here. Are we confused ourselves? So let's not confuse ourselves. Let's put y here and hx here. Okay, then this is good. Okay, we have tried to avoid all the confusion here. So is this the f we want or not? Our f have to go from A, right? But this g go from where? PHX. Somehow this GY is doing something quite we wanted already, right? So how we can modify this? Can we modify it or not? So that this G will work on A. Can we modify it? So what's our goal here? So we want to define F for something else we don't know. But it's as codomain. But we have this G here. Can we improvise a bit? So what's the hint here? So the end point here is correct already, right? Just the starting point here. So how to adjust the starting point? Can you go from A to here or not? The power set of HS. Can you do that? You go from A to the power set of HS. SHX. What is X? What does H do? So what do we have? So let me give you it more clearer. So can you go from here to here? Then go to here. That makes sense, yeah. Makes sense. So so G here do what? G here take this one to GY, which is HX. This is already what you want already, right? Something in HX. So how you start from A? How you go into power set of X? Any idea? How about the rest? Any idea? 之前 呢? 之前 seem very boring, or you got idea? No idea why you look at font. Search for answer. Any idea? Sorry? How? Tell me. How? Yeah, maybe I write here. X in A. Where should X go? Huh? Huh? How? What's the relation between A and PHX? What's the relation between A and PHX? Sorry? Sure. I mean, we want to define this mapping. But before defining this mapping, right, this two set has what relation? How do you build PHX? No idea. Any idea? What is A? A is some set, right? We don't know what set is that. What is HX? Gary, what is HX? Hey, this is not trick question. Yeah, right. So, say again. Oh, HS. So I'm asking what is H applied on X? Sorry? Function with her? No. So, okay, I think there's some misconception here. So, this should be regarded as the image of S. Okay, image of X. Correct or not? Okay. So, image of X is what? Really, image of X is just a one element, right? Okay, it's just a one element. So when I put here X equals to HX, actually doesn't quite make sense, right? Because HX is an element. Okay, so really, what do I have to do? I should draw something like this. I should understand it like this. Does it make sense? Okay. 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 So like this, like this. Okay. So go back to here. So what's this? A to P HX have to do. How to go? Sorry. Any idea? No idea. How to motivate this? So HS, what's the difference of HS and X? HS is the set. What set is that? What set is that? Don't know. What's the definition of HX? Yeah, image of X. So what's the image of X? Yeah, what's the image of X? We don't really define as a set, but a bit mouthful to say. So what is HX? Okay, so let's go back to function again. Go back to function. Say, okay, say hash is a function from A to B. Right. So given an element in the domain, okay, I can define hx. Okay, to see where does this x sends the element in A to, right? So it's an image in the codomain here. Okay. So how do we go from A to hx now? Still no idea. Any idea? No idea. Okay. So so first of all, does everyone agree that if we found this first map here, then we are quite done? Yeah. So f is not defined yet, right? We want to define f. So to define this f, right, we are lack of one more component here. What's the starting point here? What can I do? Don't know. Can we do h or not? Can we do h here? Can we do h? So if we do h, what happens? X will get sent to where? Hx, no? Right. Is hx a subset of X power cell or not? Okay. And then we can apply factorial, right? G of this thing. Such that the whole thing live in hx again. Does it make sense? Does it make sense or not? Yes. F is the composite of those two. So potentially this G, right, will depend on the X you have. So let's label like this. Okay, depend on X. Sense? The problem with the G just now is G start with a power set of Hx. It doesn't start with the original domain. So we need to bring it back right domain. Does that make sense? Okay. Any question about this one? A little bit trickier. Can.
Maybe just let x to
You instead of question you map you can, but can you do it in a consistent way or not?
each axis.
Yes, yes.
So
Fine.
there must be an empty set in PHX.
Sure, there must be, right? There exists. but can you do it consistently? How do you pick that non-empty thing? Yes, you know you can pick, but you want to define. So can you like do it consistently such that you can check on something or not? I mean, okay, this is just this is how to say you can do that. You can do that. But my question is, how do you write it down? Can you write it in a proper form or not? Because the argument you use just now is there exists, right? But what I do here is I just apply H because I know that HX always work. Yeah, I mean, yeah, sure. Yeah.
So we just I don't know.
Wait, let me think. Say again. You don't know how to write it down.
I know it exists.
Yeah.
I know this.
Yeah.
So it's also proves.
You mean you just prove existence, but you didn't write the form down? You can, but if you can write the form down, we prefer that. We prefer if you can write the form down. Yeah. A lot of theorem is like that. This, but I didn't tell you how to find it. It's better you write the form. Okay or not? Any other question? Another question before we go to the next one. Yeah. Yeah, we prefer to write the form down if you can find it. Okay. Okay, let's do 4 to 5 now before I take a break. Or let's do 4 to 5. Who is doing 4 to 5? Ziqian and Sayaka. Okay, so let me quickly see. So you have what? So you have a relation, okay, with a domain A. So just now Ziqian point out one technical thing is because we want to define a function from F, right? So we need to define for all A. Does this relation pick up all A or not? I think we should, right? So that's why they have this sentence here, relation with domain A. Then there is this subset, okay, F from A to B. But somehow you need to use part 4 here, okay? So part 4 tells you about what? About elements, membership of elements. But 5 here is a subset problem. So subset problem you can turn into a membership problem, right? So if F is a subset of raw, meaning what? Every element of F is an element of row. Okay, so from this analogy, can you find the right domain and function for part 4 to work, and then somehow you pick up your F? So what's your approach? Right? What's your approach? Yeah. Wait. Okay, so let's tell us your strategy. So we want to define this F, right? So how do you get this F? First get the H. Okay, so let's say we get the H, okay, such that is the domain of A, okay, then there is this F. Okay, so let's write down. So if we have a H from A, let's say like this, to some codomain, this implies what? There exists a F with the same domain such that fx is in hx. Okay. So so you want to define your h first. So what's your h you want now? Take h to be what? Get it? What do you mean by for every b? What do you mean by every a has a lot of b to appear? What do you mean? What are you talking about? Are you talking about function? Are you talking about relation? Are you talking about relation? Which relation you are talking about? Huh? Which given one? I give the name already. Why you don't want to mention the name? Row, right? Okay. So row is a relation, right? Okay. So what happened to this row? Why can't I take h to be this row? Why can't I take h to be this row? Can I take h to be this row or not? Sure. So there's no function, so we cannot apply part 4, is it? So how to make row a function? Doesn't make sense. What do you mean by make all the b into a set? What's the OB? Okay, so okay, good. So since you talk about definition, let's write down. Define h what? Okay, so h is going from where to where? A to B. Somewhere. Do we know the where already? Okay, sure. Let's do that. Okay. And then yeah. Okay, so let's write down. So go to y such that, so power set, right? So it should be a set. So go to the y such that what? Oh, x comma y. Okay, good. X comma y is in row. Okay, like this. Okay, makes sense. Okay, does everyone get what he's doing here? So you should imagine this row, right, is what? Set of ordered pairs. Okay, and then set of ordered pairs here, there's one property here with domain A. So meaning for every A, you will have a B attached to it. Maybe more than one B attached to one A. Okay, so what he's doing, he combine for each X, the order pair that have an X, combine all the order pair with the same X. Does it make sense? Okay, so what should I put here? So let's say example, let's say R cross R, right? Inside here, maybe row containing 0, 1, right? Maybe contain 0, 2 as well. Okay. So what does this map do? So it should sense 0 to the set containing 1 and 2. Does it make sense? Okay. Okay. So by doing this, what's the advantage of doing this? What's the advantage of doing this? Then we can use part 4 here because here become a function, right? So meaning by part 4, you will create a function such that this function is going from A to the PB such that fx equals to hx. But here we only want it to be B. F if is from A to B. Wait, let me see. Fx is in hx. Let me see, is it correct or not? Okay, so where is this hx lies? Hx lies in here, right? Hx is a subset of B, correct? Correct. Hx is a subset of, wait, so let me think, is a subset of B, correct? Correct. So I mean, so this give you, I mean, this thing lies in PB. But what we want here is a function in B. Oh, okay. Okay, I think you're right. Okay, good. Very good. So this guy is in wait, let me see. So this one should be like this, right? Okay. So fx hx is in PB. No, hx is a, you see, hx is a subset of B, right? P. Oh wait, okay. I think what you say. Okay, I just, okay, good. And okay, so I should say this one is a subset. Is it better? Okay. Okay. So here you take as a positive of B, but here you take as a B. Okay. Does it make sense? Any question? Any question?
Inside a subset of A plus B. So
Yeah.
for Y it is inside B, so it is subset of B.
What do you say? Y is a?
Y is inside B because Cartesian product. So Y is inside B, so it is a subset of B, right?
Wait, so Y is a element of B, and then Y is a subset of B. I just say again.
Subset of B. Then
Wait. So what? Which process? Which process? Definition of H. So H is what H is doing is you give me an element of X. Okay. I give you a bunch of element of Y, which is an element in B. So how do I pick this Y? Such that S and Y are the ordered pairs in row. Okay. Does it make sense? Okay. Okay. Others? The other question? Hey, by the way, you don't think that this is only one way to prove it. There's others way you can prove it also. You can much reduce this. You can reduce this H from A to PB. Maybe you just take X to one of the Y is enough. You don't need to take all Y also can, right? So meaning you pick one function out of this row, and then you do that. You apply F of this function. Also works. Okay. Okay. Any question between these two implication? Or you guys want to continue or not? You guys want to continue or take a break? I'm okay to continue if you are okay. You want to take a break? Take a break. Okay, let's take a break. Let's take a break until 1:23. Hey, yeah, Jimbo. Okay, explain it to what? Yeah, 他叫过来跟我讲，他也在。So, let's take the attendance to know. So, okay. Are you just back from visa? Because you sorry? Oh, you just arrived last weekend. Okay. Did you get all the course material recording stuff? Okay. Okay. So there's a assignment due. Did you see it? Okay. 曾思渊, Chen Siyuan. You know Chen Siyuan or not? You don't know. That's fine. Lee Pek Hong. Where's Lee Pek Hong? Sleep. 12 o'clock still sleep. Oh. Ryan. Okay. Dong Yuan. Dong Yuan go toilet. Gary. Okay. Jian Xiang. Yeah. GJ. Yeah. Ziyu. Jingbo. 丁宇、子谦、沙耶、嘉怡、OK。一兴读 class， 天科农户。啊？
红线着地啊，红线着是的。
都是你的哈，这种。
I think yeah, the car not 哎呀，前面他这个是这样子试一看看嘛，太高。应该是有人在里面，应该是那个人驾着车，然后看这样子看电话，那么滑或者是没有注意到，然后滑下去了。但是速度应该是慢的，所以人应该没有什么事啊。那速度慢，他那个车风的都太降了。是啊，对，
危险的。
哦，是那放进，包括那头跟那个是。
可能以后学校要做 handle 了。上去树林，不懂。开课的时候是吗？哦，不懂，还没有到。嗯。
empty function 有的是
啊
elenco 有些什么有这个 example
Yeah.
f 我这个function f 说 empty set 去 any set 你那个 set then 我们不是讲说我们 deduce 讲只有一个 function 那个 function 就只有 empty f maps anything 的 empty
喂，我没有讲这个，我讲的是like，如果我 understand 这个 as empty set 的话，不是 ，then 我只是 understand function and set，我没有讲这个 f 要 send 什么东西去什么东西。这个 f 就是 like 它是一个东西叫做 empty function， 它是一个东西，它是一个 set， 它是什么 set？ 它是 empty set。可是我还没有说 equivalently 它是什么东西在这边，你应该要去 try 解释一下。f 如果 as a assignment 它是什么意思？
就是说这个 empty set 如果换成 assignment
是什么？
是什么意思？OK，
但是 assignment 是说 for every element 你 assign 一个东西嘛，但是这边没有东西给你 assign。
OK，
Testing. Okay. Is everyone good? Start again. Good to start again. Okay, so let's go from 5 to 6 now. Okay, let's go from 5 to 6. Who is doing 5 to 6? Who? Jingbo. Okay, Jingbo and Yongyuan. So how to go from 5 to 6? So 6 already give you a onto map. What you want to do is you want to find a right inverse. But 5 can give you a function. Okay, so can you make use of this row here? Can you produce a row such that you can produce this f? What did you do? What did you try? Define row to be. Wait. So row is what? Row is a set of all the pairs, right? Okay, so how to write it? A, comma B. Okay, sure. Such that GB equals to A. Okay, I think this is a good choice. So meaning what? You are looking at the inverse of G. Inverse image of G. Okay, and then what? So by 5, it gives you what? An F from A to B, because this is an element in A plus B, such that F is a subset of. So what do you need to do now? Now you want to show that actually G compose F is the identity map on A. Can you do that? How do you prove this? Can you prove this? Almost immediate already. Yeah. How to write down? How to write? Huh? What do you mean by same structure? Oh, so okay, let me write down what you want to try to say. Like this. Okay, so yeah, so why is this true? Why Fa equals to B? Okay, so because okay, let me think how to write this. Since Fa equals to B as what? As how is it? Since Fa equals to B as write down as mean. Should I write anything down or not? Ah, wait, let me think. Let me think. What am I doing? Yeah, quite sure about I was trying to write thing clearly down. Let me think. Let me see. Did I write something weird? Okay, this one correct. Okay. Okay. So since I think B is nothing, right? B is just a naming here. I think the problem is with A. Why GB equals to A? FAY is equals to A. Because F is a subset of row. Sure. I mean, I can put GC also can, right? But GC also have to equal to A. So, how to say it? Because, how to write? Sorry, I was trying to relate this definition here. How to relate this definition? Okay, basically, I'm trying to transform this function of set as an assignment, right? So how to write this down properly? So for A, okay. So this assignment is like this. So FA, this one is equals to F, and if and only if what? If and only if G is 2. Does this make sense or not? Does this make sense? Sense? Yes. Okay. So here row here, right? What actually is a bigger set than F, right? Because you are considering all the inverse image. But the F here just pick up one from the inverse image. That's why it is a function. You cannot take an A and then you have bunch of B. But you just pick one B up, become a function. So that is the inverse function. Less, actually just one. Because it's a function. Right? For each A, you only have one B. Yes. Yes. Because it's the inverse image of A. Correct. That's right. That's right. Yeah. Makes sense. Makes sense. Okay. Yeah. So here actually you set your G to be what? Actually you set your G to be a map from B to A actually. Okay. And then F. The F you find is in the opposite direction. Okay. Yeah. Okay. Yeah. Okay or not? Jingpo and Yongyan. This part you have to explain well. To explain last part here. So how you go from this function definition to this property here. For a function, okay, in this A and FA form, to satisfy this row thingy, you have to have G apply on the second component, you get A. This is exactly what you want to show. Does it make sense? Okay, so this B here is actually FA, because this is how we understand function as a set. A and FA. A and then where A go? FA. Just like just now what I explained for HX. What's HX? Where the X sent by H. Image of X. Image of A. This is how we understand function as a set. A and Fx. So it's like a graph. Graph, right? X, Y. S and Fx. Yeah, it's a graph. For G here, is it a function? Yes, it's an onto function, G from B to A. Yes. G will assign to 1A. G is from B to A. G is from B to A. So 1B, you have 1A. And then?
Because we said that F, for F, you have each A assigned with 1B.
Yes.
So it's less than row, but row also 1A with 1B, then how you less than?
Wait, let me think. So what are you trying to say? So I have G, B to A, right? So 1B have 1A. Okay, good, this one. And then G is on 2, so meaning for every A, I also have 1B. Sorry? To write GP goes to A has nothing to do with this on 2 thing, I think. Wait, let me think. Yes, you are right. You are right. You are right. You are right. There's something that gets sent to A. Yeah. And then, so where's the issue here? Directly or something. Uh-huh. 之前啊 So B cross, they are what? G is not equal. Yeah, G is not equal to rho. Yeah. Yeah, G is not equal to rho. Is G. Wait, let me think. Is G equal to rho? G is equal to rho. G is equal to rho. I mean, of course, the order is swapped. Instead of BGB, you have GBB. But yeah, but A cross B and P cross A is the same. Okay. It's not the same set, but there's a bijection between them. To talk about whether set are the same or not, still different, right? Let me think. Cross N cross N. It's the same. It's not the same. Okay, it's not the same. Okay, it's just some bijection. Okay. Any other question? No, same set but bijection. But now we want to build F. Okay, we are not talking about G, but we want to build F. So that's why we look at A cross B. Any other problem? Okay, make sense or not? Make sense? Okay. All right. So let's keep going. So 6 to 2. How about 6 to 2? 6 to 2 is what? 2 is. I'm doing 6 to 2. And how about 6 to 2? Okay, so now you are given a collection of non-empty set, and then you want to find this choice function here. Okay, you want to find a choice function, but what are you given? You have these onto have a left inverse. So how do you build this choice function? Any idea? Is this the right direction you are thinking? 6 to 2. Okay, yeah. So how? Okay, so what's your B and G? What is your okay, so what's your where should I do how should I do it? Okay, so what's your B and A here? You want to build a onto function, right? Okay, so what's your B and A? B is what? B is what? You want to build a onto function, right? So that you can use part 6. Yeah. Yes, what's the domain? Collection B? You sure? So you want to have a function from A to B, right? On 6. You want to have a function from A to B. And then here you want a function from script B to the union of B. Okay. So meaning you need to have some swap here, right? To find G. Correct. G is from B to A, but F is from A to B. Okay. So B should be the union of B. Does it make sense or not? So, okay, so let me put here goal. What's your goal? Your goal is the choice function from script B to the union. Okay, this is what you want. Okay, so you're trying to get this C from this F. Does it make sense? Okay. So F is from A to B, so you have C from here to A to B. In this case, A is the script B, and then B is the union of B. So if you want to get a onto map, right? So what do you do? Okay. Okay, sure. Then what's your G then? You need to define your G then. How to define this G? So I'll put here. So how you define this G here? So how to define the onto map that works? How to define the onto map? So here is an element, right? Union of B. These are elements. So given one elements, what set you need to consider? What set you need to consider? There's one very intuitive set you can consider. This S is coming from some B, right? So in particular, you can send the S back to the set that contain X. So let's write it as a BS. We should prove that this G should do the job. Okay. Is this onto or not? Is this onto? Is this onto or not? Yes, right. Okay. Because every non-empty set is not empty, so you can pick one element in there. Okay. So actually send to the set BX. So let's see whether the hash that the question gave us will do the job or not. Okay, let's say this is the F that provide by 6. So what we need to show? We need to show that, show what? F of B will give us an element in B. Does this F do the job or not? What property you know about this F? What do you mean? I mean, from 6, right? You only know one thing that this F can do. If you compose with the G back, what do you get? What's that? It is a identity on where? On script B or on the union? The union, right? Let me see. Script B or the union? Script B, right? Is the identity on A, on the domain. Okay, so it's on the domain of F, sorry. So it's script B. So what can I do? G of F apply on B is B. Okay, but I want to show that FB is in B. Can I say anything about FB in B or not? How? Huh? By G, how?
The set that contain the element.
Okay, sorry. Yeah. Yes, G is on 2. Wait. Why suddenly you invoke inverse again? Just use G is on 2. G is on 2 means what? G is on 2 means what? So okay, let's write this down as G on FB equals to B. Okay. So G on 2 means what? If you take an element in B, right? Element in B. Am I doing something stupid or not? G. Did I do anything stupid? No, right? So so am I doing okay? So GB is on 2. Okay. So B. So what's this FB here? What's this map? G sends X to the set that contain. Right. So since G is on 2, and then this element FB here should be inside B. Okay, so we go here. This implies that FB is in B by the construction of G, and G is is this enough? I think just by construction of G, right? Construction is enough. It's enough, right? G. Don't need on 2, right? Because this is the element already. Okay, you need on 2 because it is for OB. Do you need it? Since let me think. Yeah, on 2 is already included in the identity here. Once you have an identity, then yeah. Okay, I think it's by construction is enough. Yeah, I think construction is enough. Okay, because this is how we constructed this G here. You send something inside B back to B. Yeah. Yeah. Not necessary. Yeah. So what?
Not necessarily one B containing.
Oh, you mean that? Wait, let me see. Sure. Oh, okay, I get what you mean. But I think this can be solved fairly easily. Okay, I think this can be solved. How to solve? Let's go from 2 to 1. And 1 to 2. 1 to 2. How to solve this? 2 to 1. 2 to 1, 1 to 2. 2 to 1. How to go from disjoint to how to go from disjoint to non-empty. Yeah, this is solving how to go from how do you make non-disjoint one become disjoint. Yeah, to apply 1 to 2. So how to make? So let's go to now let's go to 1 to 2. Okay, so the question that Ziqian asked just now is how to make something non-disjoint become disjoint. Okay, so let's do 1 to 2 now. So this is exactly answering that question. So how you can make something that is non-disjoint to disjoint so that you can use the original axiom options. Any idea? No idea. It's 1 to 2. It's 1 to 2. 1 to 2, right? Because 2 is non-disjoint, you want to apply 1, so you need to make it disjoint first. Make sense?
sets just by UI or just by awareness side, just to make them destroy.
Okay. So how do you define? So let's say I given a collection of P, right, of no empty set. So this one is a collection. So how do you make them disjoint?
What do you want? Didn't portion out anything that's
In the common place. In that case, shouldn't you you want to do it inductively? Is it? But the problem is you want mutually disjoint, not just everyone, not just taking out element that is in everyone, right? Mutually disjoint. Either two I pick up, they have to be disjoint. You get what I mean? Oh, you mean? Sure. I get what you mean. But somehow you need to do it inductively, right? Can you do it without inductively or not? Because here, this collection, right? We don't care whether we can label it as a countable or uncountable thing. Yeah. So you have to somehow do it at one go. Actually, this proof is in textbook. So how they make this non-disjoint, disjoint set. So they do this. So how you split these non-empty set is like this. So they define for every B a B prime, okay, such that B prime is B comma X. Okay, and then this is a subset of B script B cross with the union. Okay, and the claim is this B prime is disjoint with the rest. Okay, so first of all, right, you should notice that this set is a non-empty set. Why? Because B is non-empty. Okay. And then what? Not that. B1 doesn't equal to B2. Okay. Then B1 prime intercept B2 prime should be empty. Why? Why? Because we use B to differentiate the same X already. Okay, so let me write down the sentence here. B1 comma X1 doesn't equal to B2 comma X2, even though X1 equals to X2. So we use B to differentiate the set that containing X. We know that this 2B is not the same if the 2B is not exactly the same. So we track the difference of B by looking at the difference of elements in B. You get what I mean or not? Do you get what I mean? A
set with an element.
Okay, let me give you an example, right? Okay, let's say I give a Leong Yan. Leong Yan with this class. Just now the problem is like this. Because Leong Yan with this class, Leong Yan is also a family member with his family, right? So these are the two sets that containing Leong Yan. So just now the problem is like this. If I want to send Leong Yan back to the set containing itself, should I send it back to the family or not? Should I send it back to this classroom? Just now, Ziqian got this problem, right? Which one I need to send? Because there's two sets that containing Longyuan. No? But now what I do, I separate these two different. So, I make this two set become two different sets. How to make this different? That one is family. This one is classroom. Although they both containing Longyuan. You get what I mean? Does it make sense? You see, B1, X1 doesn't equal to B2, X2, even though X1 equals to X2. Even though both sets containing Longyuan, but these two are different sets because one is family, one is classroom. So I make this make the two sets different now. Does it make sense?
You're doing the construction
Because
you know that the issue is that they are generally they are not disjoint, and you want to make a way to differentiate, but considering you want to construct.
Yes. That's right. Originally they are not disjoint, but now I label it differently. I with a label now. This is a Longyuan with family member. This one is a Longyuan with classroom. So these are the two Longyuan. Two Longyuan now, not the same Longyuan really. Okay. Does it make sense? This is what you do so. Even though x1 equals to x2, but b1 not equal to b2. Yeah. Make sense? Okay, so this one is to differentiate. Same thing become different thing. Okay, this is kind of a trick in the mathematics. Okay, so now we got this disjoint subset already, right? We should be very happy already. Are we happy? Because by part 1, we can find a set such that what? We can find a set such that so now our collection changed already. Be careful a bit. So let's be a bit careful. So we form a new collection now. So these are all the B prime such that B in B. Okay, this is what I want to stress again. This is a collection of disjoint empty subset of B cross union of B, which this B are coming from the script B. Becomes Beethoven again. Okay. So this is the what? This is the new collection of set that we're looking at, non-disjoint one. So by axiom of choice, what do we have? The original axiom of choice. We have a set C, right? Set C, such that this C is a subset of this subset of script B Cartesian product with union of B, and then do what? When this C intersect with what? An element in here is just a singleton. So isn't that just the function, or should I? Okay, let's do it step by step. Okay, let's do it step by step. So first of all, we have this subset, and then what does this subset do? So let me write down. Second, C contains exactly one element from each set B prime. Okay, so what does this mean? That is, for every B in script B, C contains exactly one ordered pair, which is Bn, comma x. Okay, and so what's this? So this is exactly a function as a set, because we got this ordered pair. So it's a function from the collection B to the set union of P. Okay. And final thing to check is whether CB is equal to B or not, right? So this order set is our function, meaning what? Meaning this X is actually belongs to B. So that CB is in B. Okay. Yeah. Because remember how we make this X is exactly how we pick from the yeah, it's actually there you see this X here is exactly we pick from B. Okay, that's why the CB will give me something in B. This is by construction. Okay. Any question? So the key point here is this one. Okay, you get a singleton from each intersection with this element of the set. Any question? By the way, this whole proof is in Moncrief. If you want to read, have a read. Do you guys understand the construction here? So we construct a non-empty set, disjoint non-empty set from just non-empty sets, and then we check that the subset that we obtain from the axiom of choice is actually giving us a choice function. Okay. Yes, question.
Is there a
where?
Before the cross non-empty or
Disjoint non-empty or disjoint empty? Let me see. This one, huh? This one. Disjoint, right? Because we make non-disjoint one into disjoint already. Oh, non-empty, yes. Thank you. Non-empty. Okay. Yeah. First of all, if you don't understand what I fully say, right, but you need to at least get the how to say, get the skeleton first. What did I do? Okay, what did I define? And then what did I claim for this definition to work? You need to at least get these, and then you check. If you cannot check on the spot, you need to check at home. Okay, then it will speed up your checking process. Next time when people say, oh, this one got this one, oh, you straight away check on the spot. Hey, no, what you say is wrong. Okay, so you need to speed out this process, but slowly. But first thing first, you need to get what I define first, and then what I claim is true. You cannot follow the full process, but you need to pick these things up quickly. Okay, and then go back and check whether what I say is correct or not. Does that make sense? Okay. Wow, 2 already. Okay or not? Yeah. Are you guys in a rush or not? Actually, I booked this room until 2:30. So I think I want to continue because I want to do something on cardinality before we break off for the week. Okay, if you want to leave, feel free to leave because I still have recording later. Let's see. Okay, if not, I want to go to cardinality. Yeah, so this is basically about this axiom of choice. And once I prove 1 to 2, 2 to 1 is fairly easy because it's just more. Yeah. So 2 to 1, 2 is a generalization of 1. So you can apply 2. So you get 1. And then we fill out the implication. So I purposely spend this time with you and then you discuss with your friends is exactly because I want you to do it the same with your assignment. Okay. And because I might give, maybe for you, it's very hard assignment, right? So I don't want you to just do it on your own because maybe you might go somewhere else that I don't know where you are going. So try and get help from your friends. Okay, now you know at least one friend, right? At least one. Okay, so you can ask your friend just now, or you ask inside the Teams or what forum Moodles. Okay, get help from your colleague. Okay, if they don't want to help you, you can come to my office hour. Okay, Tuesday and Thursday. So on appointment, so you want to come and find me, make sure you message me first. Okay, otherwise maybe I go somewhere else. Right. Okay. Does it make sense? Okay. And in future we might go a bit faster already. So make sure you get help from your friends. It's very important. Okay. So let's leave axiom of choice for a while. Again, maybe next time we come back for a little bit more. Let's go to a new thing. So just now I mentioned idea, right? A cross B, P cross A. They might not be a same set. Okay. For example, what? R cross N and N cross R. They shouldn't be the same, right? Because as an element, their order pairs are different. But there's a notion of equality of set here. So we define for this. Now we want to go into cardinality. So we will define two sets. Okay, two sets. S and T are equivalent. Okay, we don't say they are the same. We say they are equivalent because we already have notion for the same set. If and only if they are subset inclusion of each other. But now we just say equivalent or equinumerous. Maybe this one will sound better. Same number, equinumerous, as many. If what? If there exists a bijection between them. Then we will write S tilde to T. So for example, what? 6 dogs is equinumerous to 6 cats because I can form a bijection between these two sets. But these two sets, of course, not the same. Dogs are not equal to cats. Right? You agree? Agreed. No one responded. Dogs and cats are not, different. Okay. So one proposition is very nice consequence is this equivalence, right, of set is an equivalence relation. So always we will ask if you introduce a new equivalences, are these the equivalence relation? Meaning what? Meaning you have to satisfy 3 properties. First, reflexive. Second, symmetric. Third, transitive. So are you equal to yourself or not? Definitely, right? You just use identity function as the bijection. Symmetric. If I have bijection with you, do you have bijection with me? Yes, right? Because bijection is inverse axis. Inverse of a bijection is also a bijection. You just take the inverse. Transitive. If I'm equivalent to you and you are equivalent to the others, am I equivalent to the third one? Yes, right? Because composition of bijection is still a bijection. Okay, very easy to check. Okay, next. Mission. A set
is finite, okay, if it is either empty, okay, or is equivalent to the set 1, 2 to n. There is some n in n. Okay. Otherwise, it is infinite. Actually, this is the first way you learn number, right? How are you get exposed to 1, 2, 3? Do you still remember? How do you get exposed to maths at first place? Did your parent teach you? Did your relative teach you or not? No. So instead, no. Well, what's the first instant you see number 1, 2, 3? Who tell you 1, 2, 3? Sorry. By looking your hand. Different finger, you mean?
Sometimes they are all different.
Sure. With different position, different length. Okay. So you say you discovered by yourself. Is this what you claim? Somehow? Yeah, is this what you claim? You know it by yourself? Number? I don't know. I mean, for me, it's like maybe my parents told me, like, this is 1 apple. This is 2 apples. We put 2 things here, 2 apples. But how you see 2 here? Where's the 1 here? So you attach the apple, this object, right, to some concept here. 1, 2, 3, 4, 5, 6, up to n. Okay. This is always the first example I told people when I talk about category find. Later, I will disclose more about category find. So this is the first instant, actually, how you count stuff. Okay, you attach numbers to object. Okay, for example, how we count what are the infinite stuff or non-infinite stuff. So let's say the evens number are actually as many as the natural number. Agree or not? If you agree, how you produce the bijection? Okay, so here n doesn't include 0, okay? So no 0 here. Our n no 0. And so how you make this a bijection? Sorry? 2k go to k, or the other words, k goes to k over 2. Okay? Make sense? Okay. So this is a bijection. Prove it. This is a bijection. Okay. How about let's see. An open interval to R. There's a few ways to prove this. Okay, there's a few ways to prove this. Let me show you one way to do it, at least. So what I'm trying to do is I will go from AB. Okay, so this is for any, okay, for any A and B in R. Okay, so there's a lot of ways to do this, but this is one of the way. So I'll go from AB to 0, 1, and then to 0, infinity. And then to up. So this construction also will say that all these are equivalents. Okay. So I'll send something in AB, okay, to x minus A over B minus A. Okay? You can check that whether this lies in the right domain or not. Okay. And then what I can do is, so I try to normalize everything to 0 to 1. Okay. And then what I do is I extend in one direction. Okay. And then I extend to the whole direction, to the left and to the right. Something like this. There's a lot of ways to do it, but this is one of the ways. So if I want to write them all together, it's something like this. You can check that whether this is a bijection or not. And my claim is this is a bijection. Okay. So maybe you can ask about whether closed interval is it equivalent to R or not? How about I just close on one side, close at B, close at A. Are they still equivalent or not? Yeah, you just add one element there. So this it is still infinite. Yeah. So if you still add one element to an infinite set, it's still infinite. This is one way, but there's all other way. But usually we will show 0 to 1. The interval of 0 to 1 is equivalent to R. And then from there, you can go to different interval. But how to show 0 to 1 is equivalent to R? There are a few ways to do it. In particular, there's one way to do it, right? Which way? Any idea? Arctangent, yes, that's right. Arctangent. So, still remember tangent or not? What's the tangent graph it looks like? Something like this, right? Something like this, right? Okay. So where's the R here? Actually, there's a few copy of R, right? Because you are reaching asymptote, so you are like going all over R. But you just need to pick one part of it, is enough. So what part is this? Let's say this part is from where to where? 0 to where? 90 degree, pi over 2. I think so. Pi over 2 pi and then 3 pi over 2, is it? Something like this. So pick any interval you like. Okay, but usually we pick this one, right? I think so. Pi over 2 to 3 pi over 2. Okay. So what can we do? So let me write down. So fx is going from tangent of A. So how do we pick this part? Let's say. So go from where to where? So let's build a function from 0, 1 to R. How do we make full use of this tangent function? So 0, you have to start with pi over 2, right? So how to set this function here? The 2 plus pi x. So let's try. So if I put 0 here, it starts at pi over 2. If I put 1 here, it's end at 3 pi over 2. Yeah, I think that's fine. That's fine, right? So this part is defined by this f here. So here is a tangent of x plus 1 over 2 pi. Okay, does it make sense? This is a bijection. Does it make sense? Okay, so I translate 0, 1 to this interval, and then I use f to map to all the R. And then you can, this f here, there's an inverse because it is bijection on this interval here, which is just the arctangent. Okay, make sense? Okay, so yeah, so you should think like R is like infinity, right? Actually, 0, 1 contain as many things as the whole real line. Okay. Okay, we still have 15 minutes. Any question on this? So an interval is almost as many, not almost, it's as many as a whole real numbers. Okay, this is a very important factor. Okay. Maybe it has finite length. Okay, it has finite length, but within this length, there's as many elements there. Okay, there's few more terminology here. A set S is denumerable. Denumerable means we can list it down. Okay, if S is as many as natural number, denumerable. Okay, and we will say that a set S is countable. Okay, you can count one if it is finite or denumerable. So why do I say denumerable is about listing? So you can prove a proposition that is, if S is denumerable, if and only if X element can be enumerated in a non-terminating sequence. Okay. Let's say A1, A2, up to AN. Then this sequence is called enumeration of X. Try and think about this. Does this make sense or not? So if it is denumerable means what? This set has a bijection with n. So meaning bijection with n means what? So you know n, right? N is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's a bijection meaning what? There's a one-to-one correspondence between the element of the set and natural numbers. So you just attach the label 1, 2, 3, 4, 5, 6, 7 to the element of X. So this is how you enumerate them. Okay, does it make sense? So if you can enumerate the elements inside X, meaning what? You can form this bijection. You just take the index of the sequence. Index of sense. Okay. So denumerable meaning you can list them as you list your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 down. Okay, and non-terminating, you not non-stop. If it terminate means what? Your set is actually, if the sequence terminates, mean your set is just finite set. Yes, just a finite set. Okay, make sense? Any question?
P of P set is defined to be 0.
Yes. Yes, that's right. That's right. That's right. Yes, that's right. Yeah. Yeah, we haven't actually defined cardinality yet. So I just define what is finite, what is denumerable, what is countable, and later we will introduce what is cardinality. Okay, so far okay. Okay. So next. So of course, you should expect any denumerable set is infinite. Right? Is this obvious or not? Is this obvious? Any denumerable set is infinite, meaning not finite. Is this obvious? Quite obvious, right? But how to show this actually? You really just need to show that n is not finite. Natural number is not finite. That's all. Because any denumerable set is equivalent to n. So you just say that n is not finite. Is n finite or not? Why? How to prove? By contradiction. So how to prove by contradiction? Suppose it is finite. So it's bounded by some number n. But you can find n plus 1 set. Okay. Okay, everyone is happy with this contradiction now. So let's skip this. Okay, next. So I leave it here, proved by contradiction. So next, any subset. So the problem is, maybe it's quite obvious here, but one technique here is I want to bring all the denumerable set that is equivalent to n. So I just argue on n, argue on something that I know. This is a technique here. This is a technique about proving cardinality. Okay. you have to bring it down to some set that you can control. Okay, maybe contradiction is not very interesting, but the technique here is you can bring any denumerable set. You can argue on any denumerable set just by arguing on natural number that you know how to control it. Okay. Okay. Next, any subset of a countable set is countable. Is this obvious? Is this obvious or not? Any subset of a countable set is countable. Countable means what? Either finite or enumerable. Okay. So you can just study the enumeration of your subset. If it stops somewhere for some n, then it is finite. If it doesn't stop, then it is countable. That's all. I mean, it's denumerable. So in both cases, what? It's countable. Okay, because you start with a countable set and then subset of it, meaning you maybe discard in the middle some of the terms in the sequence, but it's still an enumeration. You can relabel it. So if you study the sequence subsequence thingy, right? Subsequence, does everyone know? Subsequence, how to form a subsequence. So you have a sequence, right? And then you just pick out some of them, form a subsequence. This is something like that. Study an enumeration of a subset. Okay, next, I think this one is more interesting already. So the theorem. What theorem? Anyone want to guess? I don't know where you guess from, but we should reach this statement somehow at some stage. The set of rational number is denumerable. So there are as many rational number as a natural number. So maybe we don't have enough time for you to think. But any idea, quick idea? Any quick idea how you're going to prove this? Huh? Wait, louder a bit. Cannot hear you. Oh, you proved this. You guys actually proved this, huh? Oh, okay. Then we quickly go through it. So let's see whether my proof is the same as your proof or not. So maybe we can just enumerate the positive one first. Okay. So maybe we can arrange all the rational number like this: 1/1, 2/1, 3/1, 4/1, all the one that has the same denominator on the row, and then you increase the denominator down the column like this. Okay. And then somehow some of the fraction degenerate. For example, 4/2 doesn't appear again. So you will see a pattern like this. Right. So you need to argue that this is a sensible way to list down all the rational number. So let's focus on the positive part first. 0 is easy, right? I can simply put it in the middle. Okay. But the infinite guys are a bit trickier. So what I form is I form this snake path here. So I can form like this. Okay. And then you should argue that this enumeration will pass through every guy in the rational numbers. Okay, and so on. Okay, so it's like this. Does it make sense? Does it make sense? So you keep going on. So this is the path. Actually, this is not the only path, right? You can form any sensible path, but you cannot say I go here infinity, I go here infinity, go here infinity. Cannot. Your path shouldn't stop. Shouldn't have a middle infinity. So you should. Does it make sense of what I say? You shouldn't go to infinity and then somehow you add another sequence in. You should make a proper sequence. Okay, so you whatever path you form, it should be just one sequence. Okay, so this is the sequence I formed with this pattern here. Does it make sense of what I'm drawing here? Okay. Okay. Of course, you don't need to follow this sequence. Maybe you can do like this. Also okay. Also okay. Straight away go to here, down, and then go up, and then go down. Also can. Right. Does it make sense what I'm doing? Can or not? As long as you make it into a table first, and then you draw whatever sequence you like, so that you can enumerate them. Okay. So once I enumerate the Q plus, similarly I can enumerate the Q minus. Okay. So how to enumerate Q minus? I cannot just join the two, right? Otherwise, I have a two-headed infinity like that. So what do? So if A1, A2 is the enumeration of Q plus, okay, let's say somehow you enumerate them, then how to form a new enumeration? So one way to do it is I put 0, A1 minus A1, A2 minus A2 like that, intermediate. Not intermediate, intermittent. Okay. Yeah.
We can just use the three-side table and we
Three-side table. Yeah, you can. Yeah, that's what you mean. You mean what do you mean by three-side table? 3D, three-dimensional. So what do you mean? How do you arrange positive and negative together? You can do it, but how do you do it? Wait, no. How you arrange things first before you enumerate? So just now I arranged my positive first, right? But once you want to involve negative, so where should I place my negative? You mean on this side? Okay, and then? So where you start? So you have two infinity now, right? So where you start? You mean something like this? I think it works. It works, but a bit ugly lah. I mean, how to say? Maybe not that ugly, but you can, sure, you can, yeah, you can. Yeah. But I mean, like this is, don't you think, a bit cleaner to say, right? Otherwise, you need to take care. Oh, here infinity, come back again. Or here infinity, or come back again. Here infinity, come back again. You get what I say? Yeah, it's just a cleaner way to do it, but it's nothing wrong with that. Just that you need to argue that you will pass through everything. You will enumerate everything. Okay. 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 So can I finish up two things and then we can go leave. Okay. Let's finish two things. Because I want to put out my tutorial this week so that you can try. And then I also will put out assignment 2 as well so that you can try earlier. Otherwise, you have less time later. Okay, next one is if x is infinite, okay, then S contain a denumerable subset. Is this obvious or not? Infinite means just not finite, right? But if it contains a denumerable subset, is it obvious? Contains something that is equivalent to n. Is it obvious? Obvious. If it is obvious, how to construct it? How do you construct it? How you construct this denumerable subset? Because it says it contains one, right? So you just need to make one for me. How to construct it? How to construct? So since S is non-empty, right? Because it's infinite, then there's something there. I pick that thing out first, right? So I pick that thing out. And then, since X is not finite, right? It shouldn't just be a singleton set. It shouldn't just contain this one guy. It should exist something that is different than S1. Okay, then what do? I can pick S2 from S, take away X1. And then I keep looking at S, take away S1. Can I, S1 and S2, can I pick the S3 or not? If cannot pick, then this set is finite already. So I can pick S3 and then pick S4, keep picking. And this is my denumerable subset. Okay, so you see, this statement seemingly very obvious, but it's the construction that matters here. So how do you build this denumerable subset? Okay, so this construction is very important. Okay, maybe let's stop here. Okay, any question or not? Before we left? Question? Before we left? No? Okay, so what's the plan for next class? So the plan for next class is we have to finish cardinality. Okay, finish cardinality on next class. And then next class is on next Wednesday, the earliest, right? Wednesday and Thursday, right? Wednesday. And then my plan is for assignment 2 to due on that Friday. So meaning you got only 1 or 2 days to do it if you want to wait until I finish the topic, right? We will try the deadline first. If you cannot meet the deadline, then I can extend the deadline again. Because this deadline is due to the assignment 1. Because assignment 1, I don't want to make it to due on this Friday because maybe some of you have traveling plan, right? So I just make it due on next week for everyone. So you don't need to ask for extension. So I make assignment 1 due on next Wednesday or Thursday. I forgot. Wednesday or Thursday, yeah. And then I try to make assignment 2 due on next week, Friday as well. If cannot, then maybe extend another half week. And then we should be able to go back to track again. Friday, every Friday, we should have an assignment due. Does it make sense? Huh? Yeah. Next Monday got replacement or not? Huh? Okay, very good question. Actually, this one. Actually, I planned something here already. I try to make next Monday a replacement. So we have how many weeks? 1, 2, 3, 4. Actually, your class got 4 days to replace. One because of this Thursday here. 1, 2, 3, 4, right? We have to replace this 4 days. So I planned for 1, 2, 3, 4 already. Okay, so this is the right. So I plan to do 15, 29, and 6. And this time is a little bit different from the time now because I want to do it together with mathematical analysis. So I would do, I think, analysis from 11 to 1, and then you guys 1 to 3, like that. So this 3-day will coincide with the MA1. Does it make sense? And also, there's a secret reason why I put 15 here, 1 to 3. I hope after that day, right, if you can, okay, there will be a seminar on related to category theory stuff, categorification seminar by a new lecturer called Chris Chong. If you can try to make it to that seminar, it's after our class, 3:30. So you have 1 to 3, my class, right? And 3:30, go for the seminar if you can. Yeah, because it's about categorification. Very related to algebra. And in algebra, we try to categorize things in topology. Yeah. Maybe it won't make sense at the talk, but try and listen to some idea. Maybe next time I can bring more idea to you. Does it make sense? Yeah. So this is my little talk, okay, for you. I put class from 1 to 3 and then 3:30 maybe. If you can, okay, if you can try and attend the seminar that 15. But you stop. Okay. Make sense? Okay. I haven't booked yet, so I don't want to disclose first, but since you asked, I will try and go and book the room. Okay, so anything about assignments, you should revert back to me if there's any unsolved problem. And tutorial question, please try and do. Please try and do. And then I will release later. And in the meanwhile, if you want to ask me, you still can ask me, or you can even send me your answer whether you think this makes sense or not, that makes sense or not. You also can do that. Okay. Okay. Okay, so just anything, just let me know, okay? Don't keep to yourself, just let me know if there's anything. Yeah. I'll try to put